Hello and welcome everyone to the virtual Science Cafe. We did it. We made it. We're here. Our ever popular recurring Science Cafe that normally happens every Thursday at 7 o'clock inside the Daily Planet Cafe in downtown Raleigh at our museum is now right here on YouTube Live. Thank you so much to everyone for joining us. Know that throughout our chat today, you can leave questions and comments as we go in the chat box there on YouTube Live. We'll be checking those as we go, answering questions, and posing those to our very special guest. I do want to say, since this is the internet, please be respectful of our guest, of me, and of others inside the chat box. Let's keep it nice and sciencey, all right? Tonight's very special guest for our actual first ever virtual Science Cafe is museum astrophysicist Dr. Rachel Smith. Rachel is the head of the Astronomy and Astrophysics Research Lab at the museum and also a professor at Appalachian State University. Rachel, welcome to the show.
Hi, great to be here. Hi, everyone.
Rachel, how have you been?
Pretty good. Still working at home. So yeah, hanging in there one day at a time.
One day at a time.
Yeah.
Yeah. Thanks so much for doing this, for agreeing to join us online and
it's great.
be a part of our Science Cafe. Yeah. So
yeah.
Tonight's topic is astrobiology. So we're going to do a little bit of exploring. Astro is space, biology is life. So I guess we're talking about life in other worlds.
Yeah, we're going to talk about the search for life beyond Earth, and we're going to start on Earth and look at some really cool locations where scientists are searching for life in our solar system. And I'll talk a little bit about the research I do as an astronomer. I actually observe forming stars beyond our solar system. And we're going to use some cool software to take this virtual tour of space. And I'll tell you all about that too. So I hope it's fun for people. I hope we all feel like we left our houses a little bit with this journey tonight.
I am ready to escape Earth for a few minutes.
Yeah, space is looking pretty good right now, right?
Let's just all get in the shuttle and take off.
All right, so let's get started. Okay, and by the way, behind me, I'll just say this is the inside of a telescope that I use called the Infrared Telescope Facility, and it's on Mauna Kea in Hawaii. And I put it behind me to remind me of those great days when I go observing, and I will tell you all about that too. So this may look recognizable. This is the Grand Canyon, and everything I'm going to show you tonight about the search for life beyond Earth is we're visualizing everything with software called OpenSpace. And the link to this software, it's free, it's open source. It's a project that the Museum of Natural Sciences and some other institutions are partnering with the American Museum of Natural History in New York. I hope you're watching. Hi, New York. And so we're part of this project to create some programs for everyone. So I hope you enjoy this one. This is the theme of astrobiology, but you can go anywhere you want in space, go explore Earth and explore beyond Earth. And everything you see is based on real data. So all of this imagery, this is the Grand Canyon. We're in Arizona. And all of the imagery you see from Earth and beyond is based on data taken from satellites. It's all real data rendered in this software. And so we're going to start with this canyon. Why? Because it's really amazing looking. That's the first thing. And also, we're going to talk a little bit about other planets that have similar geology to Earth. We're interested in where life could be. We're interested in maybe going to other planets someday, like Mars. And the Grand Canyon is a great place to start on Earth to think about this canyon when we go to Mars and look at another canyon. So the Grand Canyon preserves millions of years of Earth's geology. It's carved by the Colorado River, which you can see here. You can zoom down even closer, in fact. And just fly around. All the visuals I hope they're coming through okay for everyone. Know that if it looks a little laggy, some of that's the internet transfer of information, but at home, you might see it a little smoother, so you can see and really important aspects of Earth's history. So we're in Arizona now, and one of my favorite places in Arizona is Meteor Crater. So I'm going to bring up our toolbar here, and we'll go to Meteor Crater. I'll make a little bubble. We'll just swing on over here. We're going to go kind of fast. We're often going to break Einstein's rules of relativity and go faster than the speed of light when we go to other planets. But we're going to zoom down here. That makes a little. This is my bookmark, this artificial sphere, but we can turn that off. And we're going to go down to Meteor Crater. So Meteor Crater will stop here a little bit above the surface. Meteor Crater is the result of an asteroid impact that happened about 50,000 years ago in the Pleistocene. And it's one of the best preserved craters we have on Earth. And it is one of the representations we have of how asteroids hit our planet. We had an asteroid impact in Russia a few years ago. And really the history of Earth owes itself a lot to asteroid impacts, whether it's extinction events or possibly bringing important materials for life on Earth, like water and other molecules. So this happened 50,000 years ago during the Pleistocene. And during the Pleistocene, I'm going to show a few slides. What my first image here to show you is that we had woolly mammoths here and, woolly mammoth. And giant sloths. So these are some of the Ice Age mammals that are not alive anymore. But in this region of North America, it was much wetter and cooler. And so giant sloths and woolly mammoths existed around here. They wouldn't have gone extinct from this impact, but they certainly were around to perhaps witness it. So we think about impacts. There are a lot of impacts on other planets. Most of the stuff that comes down to Earth gets burned up in our atmosphere, but we do have this really awesome crater. There's a visitor center here, and you can walk around the crater if you ever visit Meteor Crater. They also trained the Apollo astronauts in this crater to learn how to recognize impact craters on the moon when they went there. And we just had a great anniversary of the Apollo 11 landing, so that was pretty cool last year. So this is Meteor Crater, and now we're gonna zoom out a little bit, and we're going to leave Arizona. You can see that really nice. Some of this looks just like what you see from an airplane. These stars are magnified a little bit, but they're all where they should be for this day and time. And we're going to go to Mauna Kea in Hawaii. And I'll tell you why. Let's see, Mauna Kea. We'll swing around and go to, I think we have to turn the globe around a little bit. There we go. Should be pretty nice and light in Hawaii now, so we don't have to turn the sun on for them. But this is Mauna Kea. This is on the big island of Hawaii. And there are 13 working observatories on Mauna Kea. So when I go observing, I'm fortunate, very fortunate to have great colleagues and have opportunities to observe on this mountain. I just will stop for a second. This is called a shield volcano. This is not an active volcano, or it has a small chance of being active. The real active volcano is down south here in Hilo. This is called a shield volcano. This is the same exact kind of volcano as we see on Mars, and we'll go to that next, actually, Olympus Mons. We have similar processes on Earth as on Mars, and we're going to talk a little bit about that in a second. So this is a shield volcano. The observatories are right here, and these little things that look like anthills are actually called cinder cones, and they are the product of volcanism as well. You can start to make out these telescopes. And I absolutely love going up to the summit of Mauna Kea. I was there last year for observing, and took some pictures of that of this region. So here is, we'll pull down here. And the telescope I use, these two domes are the Keck telescopes, and this little telescope, which I've been working with recently, is the Infrared Telescope Facility. And this telescope was built in the it was built in the 70s to support the Voyager mission, which is now on its way to interstellar space. So we'll stop about here, and I'm going to show you, we'll take a little pause with OpenSpace, and I'll show you a few pictures from observing, so you can kind of get an idea, hopefully, of what I do as an astronomer. So giant sloth. So first of all, when you stay as an astronomer going to observe at the summit, it's a really awesome opportunity. It's one of my favorite things to do as a scientist. Is you stay at this lodge area, which is about at 9,000 feet elevation. On the summit, we're at 14,000 feet elevation, and you'll see in the foreground this little plant called the Mauna Kea silver sword. I bring it up because it's one of these. It's one of these special plants that's a kind of, it's not quite as extreme as the life we think we might find in space, but it sure is a hardy plant that has learned to survive, or has evolved to survive, I should say, in these harsh conditions on Mauna Kea. It is very endangered. They're having trouble bringing it back, but you can go visit it at a certain designated area where they're trying to keep it going. And you wipe your feet here, open this little gate, and walk around and see the silver sword, it's a really beautiful plant. And it reminds me of maybe one day, if we ever get to Mars, terraform Mars, perhaps in many, many years, thousands of years, it would probably take, maybe some life like this would be the first kind of plants we would ever find. It lives 15 to maybe 50 years. And once it blooms like this is the flowering phase, it then dies. So it has a sad ending. But eventually you get more silver swords, and they really are pretty cool. So with driving up, this is we're above, astronomers want to be in these high, dry places. So on Mauna Kea, we're above the marine layer. You can see these clouds here. And this is what the telescope looks like up close. And standing in front of it, I'm just going to go through kind of quickly because I want to take you guys out to beyond the solar system. So we don't want to spend too much time in here. But this is the inside of the telescope, similar to what you see behind me, where the dome is behind me, just to give you a sense of scale. This is a 3-meter telescope across the diameter of the mirror. It's kept very cold. This is liquid nitrogen to keep it cold in there. We're doing infrared astronomy, so we want it cold inside so the heat doesn't get in the way of our science. And it's for scale, so you can see a human scale there. I am a human in spite of what you may have heard. But so this is inside the dome. And then when we observe, we're not in the dome itself, we're right in an adjacent room. And this is what it looks like. We use these computers to manage to move the telescope and to take our data. And here, right here, you can see taking some data in there. We have a telescope operator who's monitoring everything from the weather to what's happening with the instruments and the dome. And it's a pretty sophisticated operation to use one of these big telescopes. And this is just one example of the picture. You can take this as a forming star with winds blowing out of it, and it's very hot in near the star and cold outside the star. And this is what the data would look like. And we have atmosphere, we have the Earth's atmosphere, and then a line. And this is why we go up there. These lines, which may not look as exciting as, say, the picture of the star or Mars or something, they're actually really great pieces of information for trying to understand the chemistry of these stars. This connects to astrobiology because this is looking at carbon chemistry of these stars and trying to understand the chemistry that we need to form planets and important molecules. So afterwards, there's, of course, beautiful sunrises, also sunsets, and you get some really nice views when you're up there. You don't even need a filter. This is how it looks up on Mauna Kea. All right, so we're gonna now leave our slides, and we're going to zoom out and go back to our virtual spaceship and go to Mars. So here we go. And we're gonna get there really fast. To send an actual human to Mars on a spaceship would probably take about 8 months to a year. We're not really there yet, being able to do that. So here's Mars. What you'll see as far as data, when we're gathering all the data for these planets, it's a lot of information, and some data sets, we don't have a complete set of data in the program. So you'll see these little strips. It's just an aspect of how scientists visualize planets. So these strips are just part of the data visualization process. But we're going to zoom down a little bit, and actually I'm going to take you to that volcano. So we went from one shield volcano to another one. Oops, spelled that wrong. There we go. And we'll swing around, and here it is. I may have to make it a little brighter for us. So to make it brighter, I'm just going to change the time so you can manipulate time, and you can manipulate data sets much more than I'm going to show you today, but you can have a lot of fun with the solar system with OpenSpace. So this is a shield volcano that, again, same kind of formation. The shield volcanoes are named because they resemble a warrior shield. They're very flat domes. And this volcano is we think, just how Mauna Kea formed as well. And we have some really, really nice visuals of this. This is called a caldera. The data we get for Mars, most of the data I'll show you are from the orbiter around Mars now, called the Mars Reconnaissance Orbiter. And this orbiter is providing all of these really amazing data sets that I'm going to show you today. So you can take a tour around here, and when you look at Mars, think we formed the same way Mars did, and all the other planets. And Mars is a terrestrial planet. It has a surface, and we hope to one day send astronauts there. So this is the largest volcano in the solar system, and is a very shallow volcano. So if you were standing there as a human scale, you wouldn't even see from end to end of this volcano. And this is Mars's thin atmosphere, which is about, it's a very thin atmosphere, about 30% of Earth's. So we're going to go now sorry for the short stop here, but we want to see a few more places. And we're going to go to Valles Marineris. So remember the Grand Canyon that we went to. We're now going to go to one of the largest canyons in the solar system, and you can see it from space. It's asleep right now, so we're gonna make it. Everyone gets morning with this program. So here we go. So Valles Marineris is about the width of the United States. Mars is a smaller planet than Earth, and it formed a little differently than the Grand Canyon. We don't think it formed just from water flow like a river. It formed from a combination, most likely, of volcanism. It could be a crack in Mars's surface from tectonic activity. So like we get earthquakes, plates pulling apart, and Valles Marineris is one of these really fascinating geologic features of the solar system. With OpenSpace, you can get down really close. There are some high resolution data sets, some patches in here. You can turn it around. So if you want to fly through the canyon, you can do that. And you can get down pretty close. And it may take a little while for data. Oops, our plane isn't behaving. And again, remember, so it feels, if you're watching on a big screen, or even you can see this in planetariums, is even on your computer, it almost feels like you're there because of the quality of the data. It may be a little blurry for you right now because it hasn't necessarily all loaded in. You might see it starting to come in. But Valles Marineris, as a comparison to Earth, is pretty interesting, and we can use what we know about Earth's geology to study Mars and other planets. And we have rovers on Mars, we have robots on Mars, and we eventually want to send humans to Mars. And so we really want to understand as much as possible about Mars in order to do that well. And maybe in the future, we'll have a colony on Mars. But here you can fly around, you can go all the way through this canyon. We haven't yet landed anything in this canyon, but hopefully one day. So 2 more quick stops on Mars. The first one is a really interesting, is a really interesting outflow channel where water flowed. So one thing to know about Mars is that we are certain that water flowed on its surface at one point in the past. And for astrobiology, that's really important, because where there's water, there could be life. And so Mars could have been habitable with some kind of life sometime in the past. We're not sure if that's true, and we don't even know if there's life under the surface of Mars. And it's possible that there's water flowing periodically comes to the surface of Mars. But there's this outflow. Oops, I think there we go. You can see this outflow, this long region here, this river that is an outflow channel, and it's going down into it's flowing this way, north to south, and this is just one of many features on Mars where we are which show that water existed in the past. You can get down pretty close to it, and it's a really important feature for studying. It's an important region to know about if we ever want to look further for fossil life, maybe even this would be a great place for life to exist, maybe even under the surface. But so far as we know, we're the only planet with life, and we're still looking. So this, again, this is one of the features where water did flow in the past. And the last place on Mars we're going to go to is called Nili Patera, and it's not formed from water, but rather wind. And let's see, where's Nili Patera? And it's a pretty spectacular region. So there it is. We'll get a little closer. And then we'll switch to get the, let's see, bear with me here. Driving and talking, it's a skill. Maybe. I don't yet have it, but I'll get there. All right, so we're going to wake up Nili Patera, and in order to send humans eventually to Mars, we want to understand all the weather on Mars now, and Mars does have many features that are due to wind as well as water, and you can see these are aeolian features right here. These little circles with flows that would look like something coming in one direction, probably a combination of water and wind, but it's right next to this dune field, which we're going to go to in a second. But these little features are also related to wind and maybe a combination of water too. So if we want to land humans on Mars and eventually set up even a colony on Mars, we have to understand how the wind could affect the surface now. So I'll take you down right here. So this is a square. There isn't this square on Mars. It's not marked out by any kind of alien civilization or anything. What you see here, this is also this region here, which looks a little lighter than this. This is also Nili Patera, but this little strip is a really high resolution data set that we have from the orbiter. So you'll see the difference when we go down. And one thing, if you're interested, if anyone out there is interested in how scientists visualize surfaces and visualize planets and visualize even places we haven't traveled to beyond our solar system, OpenSpace is a great way to start thinking about that, if you haven't already. And I'm trying to roll this. Come on. There we go. Thought we could fly over this dune field. The dark regions are probably, we think, ancient lava flows, the sand from old volcanic material, and the lighter regions could be also volcanic in origin. But you can see, you can fly over. It's an incredible amount of detail, and all of this entire field is shaped by wind. And we may think, if you've ever been to a dune field like White Sands, there's some similar aspects to this you can see. And so we understand, planetary scientists understand how wind affects surfaces, and therefore we can understand more about what we see on other planets. So you can see Mars's atmosphere there, and take a little trip over this dune field. It's one of my favorite places on Mars. It's just so stunning. And all of this is as real as we can see it at this point in time. All right, well, we're gonna have to say goodbye to Mars, unfortunately. So let's zoom out. And we're going to go to the largest planet by far in our solar system. We're gonna skip on over to Jupiter, specifically Europa, which is a moon of Jupiter. And so we're not gonna really spend too much time. Oops. We're not going to spend too much time at Jupiter. We're going to fly by it, say hello as it goes by. Hi, Jupiter. There it is. Giant red spot. That's probably a storm. Keep on going. This is the Milky Way. You see all these stars are where they're supposed to be. Really cool. All these star fields, you can see their colors, and they all have meaningful scientific information in there, which we won't have time to cover today. This is Europa. This is one of the most interesting moons of there's Jupiter in the background, moons of our solar system, because we think there's a global ocean under the surface. And again, ocean, flowing water, liquid water could mean life. The ocean is kept liquid. It's very cold here. The ocean is kept liquid by Jupiter, because Jupiter is so big that it pulls on this planet, on this moon, just like our moon pulls on us and creates tides. What happens is that Jupiter pulls on Europa, to keep this ocean, this water underneath this ice in a liquid form. We think, and we're sending some more missions there. Europa Clipper is going to go to Europa within, hopefully in the 2020s, and explore this surface, at least from above. We don't yet have a lander that can go, and hopefully one day. These cracks are due to salt coming up from what's a briny ocean up underneath the surface through the ice. And when we think of the type of life that could live on this planet, on this moon, we think of these extreme microbes that could live, that we know exist on Earth. And we're going to end in one of these places where these microbes exist on Earth, in the United States, in fact, perhaps some of your close neighbors. But you'll see when we end there. And microbes like that, or microbes like what live underneath the ocean in these deep sea vents, could potentially live on Europa. So this is a really important moon for astrobiology, and maybe we'll find some life there, or if not, just learn more about our solar system. Okay, we're going to take another exciting trip in our virtual spaceship to Enceladus. When we think about icy moons and water, we're thinking about, we can't not mention Enceladus, which is a moon of Saturn. So it's even colder out here. Here's Saturn. Let's take a quick look. Saturn is amazing. Saturn has these gorgeous rings. And this is imagery from Cassini, the Cassini mission. It has a hexagonal storm on its surface, on North Pole. We're not exactly sure what's going on there, but we're going to have to just swing on by. You can explore it more on your own if you want to download OpenSpace and try it. This is Enceladus, so it may not look that much different than Europa, but it does have liquid water somewhere, because scientists have found plumes of water spewing out from the poles of Enceladus. And so water and bits of rock, we know that there's some ocean under here. And so hopefully one day, this is Saturn swinging around behind it, one day we'll be able to explore the ocean on Enceladus. And I will mention one more moon of Saturn that's a little bit different, and that's Titan. And Titan's pretty fascinating. It's one of the most interesting moons in our solar system. Titan is interesting for two reasons. There's no liquid water, we think, on Titan because it's too cold. But these data here, these dark patches are lakes of what are called hydrocarbons, like methane or ethane. And these are liquid molecules that have carbon in them, but are liquid on the surface. And so it's been hypothesized that maybe there's some life, because all life as we know it uses carbon, is carbon based, and all life as we know it so far needs liquid water at some point in its life. But on Titan, maybe there's some way life could survive in a liquid hydrocarbon environment. And so there's many studies to explore the possibilities of life in these hydrocarbon lakes, which are these dark patches. And so Titan's really fascinating. The second reason Titan's pretty cool is that it has a thick nitrogen atmosphere. It's the only moon with a thick atmosphere in our solar system, and the only moon with liquid of any type on its surface. And it resembles our early Earth from billions of years ago. And so studying Titan helps us understand more about our own evolution as a planet and the evolution of life on this planet. And so Titan's really fascinating. There's a mission called Dragonfly that's going back to Titan pretty soon. Well, in the next 10 years, which is soon, by human space exploration standards. Not by geologic time, or universal time. But okay, so this is Titan, a really awesome little moon. And we are, the last stop before we go back to Earth is our radiosphere. And this is where we start talking about extraterrestrial intelligence. Because the radiosphere, this grid that I just pulled up, I'm zooming out past our solar system. Our radiosphere is as far as we've sent signals from radio and television beyond our planet. And the radius of the radiosphere is about 100 years, 80 to 100 years. So the diameter is about 200 years. And any civilization that could know of our existence would have to be within this sphere to find out that we exist. We have not yet none of our signals have gone farther than this. This is the speed of light, and as far as we've been able to send signals as a technological, civilization. So let's zoom out a little bit to see how far this is in context. Pardon me. So here's our radiosphere. We're inside it. Don't forget. Now we're going past our radiosphere, well past our solar system. Here's our galaxy. So keep in mind, this is our radiosphere. These are stars. We're one of billions of stars, a few hundred billion stars in our galaxy. And we're one of a few hundred billion galaxies. Excuse me. So this is our radiosphere. We're going to pull back. And you'll see just a few of the billions of galaxies. Just a few. So we have not sent signals very far. Oh, I swallowed something. Very far at all. And so keep this in mind when we're thinking about extraterrestrial intelligence, is that we have not been able to either send signals or explore very far. But we're trying. And if there are aliens out there, they could be out there. There's a lot of possibility, but they'd likely be very far away from us. Even if they're on the other side, here we are. If they're on the other side of the galaxy, they could be 80,000 light years from us or 70,000 light years from us. So that's a really long time. It would take 70,000 years for light to get there. Remember, we've only been sending signals for 80 years, and it weakens as it goes out. The signal weakens, and then it would take another 70,000 years for a signal to come back at the speed of light. So we have a long time to wait, but there's a possibility. And so we should look, I think. We should keep looking. But still no evidence for aliens of any kind, whether microbial or little green men and women. So the last stop, we're going to go really fast back to Earth. And the very last stop relates to what I was saying on Europa. And these are the salt ponds in San Francisco. So let's go back there, and then I will. We're going to end in San Francisco and look at these really cool salt ponds, which you can see from an airplane if you fly into the San Francisco airport. And this is where microbes live that are harvested for salt. They're called halophiles. They love salt, and they create these amazing colors. And this is the type of organism that could be like what we could find in space. So let's find it. It may be getting dark, so we'll wake it up. San Francisco salt flats. Shouldn't be that dark, California. No, it may be gone. Oops, there it is. It's on the other side. All right, so we'll zoom down here. So you can see it's night. We have nice Earth at night, but we'll look at them during the day. All right, let's just make it light. Wake up San Francisco. Hello. All right. And we'll go ahead and zoom back down. There they are. So maybe on Europa, there's some halophiles, these microbes that make these beautiful colors. And these colors are from enzymes because it's really salty in these ponds and they need special features to survive. And very few organisms can survive in this salt. But these halophiles can. And so this is the type of extreme life where we can, which scientists study now to motivate their search for life in space. So that is our brief astrobiology tour. And I think we now have time for questions, Chris. So I hope everyone enjoyed our quick tour of the universe, or not even, just to the radiosphere and a little bit beyond. And also encourage everybody, while you're home, try out OpenSpace and take journeys of your own. You can go from Earth to the cosmic microwave background. So it's a lot of fun. All right.
Thank you very much, Rachel.
You are very welcome.
Everyone at home on your computers, give Rachel a big round of applause.
Yay, I hear it.
That was fantastic.
Thank you.
You can hear it all the way from there.
Oh, yeah.
This is cool stuff. OpenSpace is amazing. I have it on my computer, and it is fun just to fly all over the universe, visit galaxies, or look at the details of planets in our own solar system, just to explore all the tools that are available. It's a pretty amazing product.
Yeah, there's a lot to see. And what I love, should I stop the sharing here. I guess I can for a little bit so we can chat. Um, it is. And one thing that I love doing is you can play around with data sets. You can turn things on and off. And so you can turn atmospheres on, you can turn data sets on and off that show how the features change. And so it's really very interesting to see different aspects of a planet. You can turn on, I didn't show people this, but you can turn on elevation maps. So you can see the elevation in different colors, where like blue is low elevation and red is high elevation. And that's a lot of fun. And it actually, you learn a lot. I mean, I learned from OpenSpace. So it is a lot of fun.
So I'm going to remind everybody, if you have questions, comments, put those in the chat box. They're on YouTube. And as they come in, we'll post those and I'll pose them to Rachel. I'll give you folks a few minutes to gather your thoughts on astrobiology and everything you've seen and learned. But Rachel, I'm curious, you talked a little bit about the research that you do on forming stars. How does that connect with your interest in astrobiology?
Yeah, that's a good question. I've always been interested in astronomy. I've always been interested in astrobiology and knowing if we're alone in the universe. My specific research project, my projects connect more to the chemistry before planets form. So in order to understand the whole picture of where do we fit in the universe, where does our planet fit in terms of a context of having life, and let alone intelligent life, we need to understand the chemistry. And I really like the kind of work I do with spectroscopy, where I showed you the little lines and we can analyze in great detail the chemistry of these forming systems, is to understand these chemical pathways better that will eventually lead to planets, because we think that every star should have at least one planet, and understand how the molecules form that are important for forming life. And so while I'm not searching for life specifically, the kind of work I do where I observe with these really awesome tools that we have. I mean, Mauna Kea is the best site for observing on Earth. So I feel like I'm in sort of this virtual kind of a spaceship in and of itself, but just being on the top of this mountain with these amazing tools is that, we get to learn a lot about these forming systems by doing this kind of work with telescopes. So I just find it fascinating for lots of reasons: the connection to astrobiology, and also the collecting of data, the way we do it as astronomers, and the amazing access we have to very detailed information using the tools we've invented. So it's pretty cool for a lot of reasons, I guess.
All right, so I'm going to toss you some questions from the chat.
All right, awesome.
Tanya was asking, is there really water on Titan?
No, there's not liquid water like H2O, but there is liquid methane and ethane and other hydrocarbons. So it's a liquid of other molecules, but not liquid water, because it's much too cold for liquid water on Titan.
Okay, so how do we know what the lakes are made of on Titan?
Well, because we had the orbiter. Well, there was Cassini was around Saturn and took there was spectroscopy done. So you'd have instruments that can tell you the composition of surfaces, and so you can actually do, using various tools on orbiters and satellites, we know the chemistry of these surfaces of materials on the surface. And there was also a lander called the Huygens probe that was landed on Titan, a really amazing mission, part of Cassini. And it landed and took really detailed information of the surface. They wanted to land, actually, as far as I understand, the scientists wanted to land in one of the liquid lakes, but ended up on a solid surface. But nevertheless got some really detailed information of the surface chemistry, just like we do on Mars now with the rovers on Mars.
The North Carolina Office of Environmental Education posted a question.
Yeah.
How can astrobiology help us learn more about Earth and the future of life on Earth?
Yeah, it's a great question. Well, I should say that everything we study beyond Earth teaches us more about ourselves on Earth. And there are many examples of this, but in terms of astrobiology, there are many. Well, first of all, the evolution of life, the early Earth. If we want an analog to the early Earth, we have Titan, for instance. Mars lost its atmosphere. It did have a magnetic field. It had an atmosphere at one time because it had liquid water on the surface. How did it lose its atmosphere? Could we lose our atmosphere? We know that it's probably due to the solar wind bombarding the atmosphere on Mars and kicking off all the molecules. So Mars doesn't have an atmosphere to hold on to water. And then you can go back, then go closer to the sun to Venus, and Venus has a runaway greenhouse. So this runaway greenhouse effect on Venus, which is a sobering future for us, possibly, if climate change isn't kept under control, is you get this very this searing hothouse of Venus, and we know that that's due to this greenhouse effect that's out of control for reasons, other reasons than on Earth. It's not because of there are no humans doing that on Venus, but it has to do with the fact that Venus doesn't have the tectonic activity that Earth had. But it's an example of what would happen if a greenhouse goes out of control. And there are many other examples. If we think about in terms of the future of humans, where are we going to go if we want to leave this planet? If we're thinking about colonizing another planet, we have to know what's happening on these planets. So Mars, if we want to send humans and set up a colony on Mars someday, the future of our species, we have to make these baby steps to go to Mars and then eventually beyond the stars. We have to do a lot of things first, but one thing is we have to understand what's happening on Mars now. Could we ever terraform this planet? And we take a lot of technology we don't have right now. We haven't invented yet. And we think about, we want to terraform a planet to create an atmosphere, which takes a lot of control, but our atmosphere is a little out of control. So, there are a lot of things to learn from other planets and even other stars. We're just continually learning, and it is important to remember that we are still learning a lot about Earth. We want to know about extreme life on other planets, if there is any, and if there isn't any life discovered, that also tells us something about Earth, right? And it tells us about us as a species, right? And even if we find nothing, we learn a lot.
Right. That's mind-boggling. Just incredible stuff. Okay, I've got more questions coming in. Let's see. Wes wants to know, is there any space that we've discovered outside of our solar system? Do we know anything about planets or the surfaces of planets maybe outside of our own system?
You mean we haven't gone to any planets outside our solar system, but we certainly have discovered many exoplanets. So any planet beyond the solar system. And sure, we know a lot about exoplanets. There are these quote unquote Earth-like planets because they don't have life like Earth. We don't know if they do or not, but they might have liquid water on the surface. And we discovered many kinds of planetary systems, very different from ours, and with telescopes and satellites. And so we haven't, the farthest we've ever moved or journeyed out from our planet is the Voyager probe. We've sent from Earth is the Voyager probe, and that is now between the end. It's basically on its way to what we call the Oort cloud, which is where our long period comets come from. So it's going to get to interstellar space in maybe 30,000 years or so. But we know that there are lots of exoplanets out there. There's a few 20 or so that could be habitable, but we can't get there physically yet. We can't even really send a probe there yet. Maybe someday. But we know a lot of galaxies. Certainly, we know we've even observed to the edge of the visible universe. So, yeah, you don't have to send a robot, but we have telescopes and stuff.
Cool. Ready for the next one?
Yeah.
Cool. You're doing a great job. Elizabeth Green, how tall are the dunes on Mars?
I thought it was going to be like, how tall am I? Like, that's not relevant, but okay. That's a good, how tall are the dunes? It's a great question. I don't actually know that answer. But given the resolution, I'm just thinking, I'm visualizing them in my head. I don't think they seem very tall. I would imagine you could walk over them, but don't quote me on that. It's a great question. There are a lot of dunes, though. If you mean the ones I showed you, like Nili Patera,
Right.
they didn't seem very tall because we were really close to the surface and they looked rather shallow. There are taller dunes, but that's a great question. I should know that number, but I don't. I'm pretty sure they're shallow, and if you could walk on them, you could probably walk over them. Yeah.
A different Rachel Smith is asking if you
Oh,
can use OpenSpace for educational programming, kind of like this for
mhm.
doing public programs.
I'm sorry. Can you? Is that the question?
I think so. Yes.
Yeah, you can use, and I teach astrobiology and another course at Appalachian State, and I use it in my teaching too. So if you're talking even about not just public programs, which is it's great for, as you can see, for and you can create many themes around it. If it's not just you could just do a regular tour, like let's travel around and look at some things, or you could do a thematic program. But I also use it in my class. So we were studying Mars today, actually, and instead of showing slide after slide of images of Mars, I've shown them open space of Mars because they can travel around and then the students can go home and download it. Actually, they are at home now, so they could do it right then. But in general, it's a great tool, especially because it's open source. And we enable that to happen, by the way, because it's partially funded by NASA, and so this is a funded project to create free software for everybody, for educators, for scientists, for the general public, for anybody who wants to use it. So that funding has helped this to happen to create this tool. I found it really useful in lots of ways.
Looks like user J Dozier, hope
Mhm.
I got that right, asks, do you expect the James Webb Telescope to impact our knowledge more so than the orbiters?
Oh, well, it depends on what kind of knowledge. It will definitely impact our knowledge on the infrared universe. So it will open up this entire window of infrared astronomy in the universe. So exoplanets, places we can't send orbiters. So if you could send an orbiter to every exoplanet, you might get more information than James Webb. But James, we can't do that. So James Webb is going to be fantastic as a complement, as the next generation from the Hubble telescope. It's going to enable so much science that we haven't been able to do, just because Hubble was mostly optical, and then and a few other wavelengths, and then but James Webb is going to open up this window into infrared in looking farther, and so it's going to be really amazing, for beyond the solar system.
You're knocking these out of the park.
Oh, thanks, Chris.
What's your favorite answer to the Fermi paradox?
Oh, right, the Fermi Paradox. So that is, if people don't know, where is
Help me out.
everybody? Where's everybody? Not just in your house, nobody's in your house, hopefully, that shouldn't be there, but where is everybody in general out there? There's so many planets, so much life, or not so much life, but so many molecules. This was presented in the 60s by a physicist, 1960s, which is the idea of where is everybody if there's so much out there. So one answer is we're alone. And I don't believe that. I mean, this is my feeling, right? So this is not based on, we don't know the answer of where is everybody. Um, I don't think we're alone. I think that's highly improbable. I don't know this to be true, but I don't think so. My feeling about it, knowing all that's out there, is that there very well could be life out there, but it's so far away. And Carl Sagan had this great quote that it resonates a lot with how I think about it, is space is vast and the stars are far apart. So just like I was showing with the radio sphere, even our own little galaxy, 70,000 years or 100,000 years to get from one end to the other, that's 100,000 years to send a light signal, let alone a spaceship. And then 100,000 years to get back. And so Carl Sagan thought, well, sure, there could be. He was a big proponent of SETI and the search for extraterrestrial intelligence and sending probes. He put those golden records on the Voyager probes in the hope that, in the very off chance that an alien civilization would find it well after we're gone, could be millions of years from now, to see that we existed, just as a part of this idea, I guess, of a galactic communication that doesn't even really benefit us because we probably wouldn't be here. So I think that makes sense to me, that there could be some in our neighboring galaxy, which we can't even get to remotely close get to. We can't even leave our solar system. there very well could be a civilization, could be a people like probably more advanced than us, but we won't know about it. And it's a sobering idea. But I think if we really want to know about it, if we decide as a society, a human society, to know about it, we've got to support the technology to get us there. And it's hard to think in those terms because it takes a lot of steps to keep building that technology up. In terms of travel, right now we just use rockets, which aren't going to get us very far at all. You need other types of power, other types of ways of traveling through space. So my answer is they're probably there, maybe, but not we're not going to know. I think maybe it'll be very hard to know if they're and so far, but yeah. So we don't know yet. We may never know, but I would say the likelihood is that we're not alone in this entire universe. So I think that would be very strange to think about, but it wouldn't make a lot of sense to me. But again, we don't have that answer. This is just my thought.
There you go, David. There you go.
Yeah.
Let's see. Actually, this next question kind of relates to what you were just talking about. Eric Dorfman is asking,
Oh.
is there anything we can do to get around the vast distances in space and travel or explore other areas of the universe?
Yeah, that would be great to do. To get around, we'd have to develop technology to get us there. So rockets aren't going to do it. There's nuclear technology, which is shrouded in a social. There are social issues to that. You could there's For interstellar travel, there are ideas out there, matter antimatter. So like if you have a molecule, it's we don't know how to do this. They've looked at this with a few particles. It's the essence of it is that converting matter to energy, you could have complete conversion of matter to energy, well beyond the energy in a nuclear bomb. If we can develop that technology, that could get us to the stars. There's this idea, there's something called an Alcubierre warp drive, which is a theoretical drive that's just like you think about in Star Trek, where in fact he took the name, the person in charge of this took the name from Star Trek, in fact, where you pull space towards you, you somehow warp space and pull it towards you. So it simulates going faster than light, speed of light, but you're actually moving space towards you. Wormholes are possible. They're theoretically possible, but we'd have to figure out how to create them so they don't collapse on themselves. This is really advanced technology. I think that if we really want to do it as a society, we have to keep moving forward and inching forward to these new technologies, not relying on rockets, which aren't going to do it, but thinking about getting there faster with humans. And I would hope that that people go versus just robots. That's my hope. I think, there's a lot of debate about that. But that's a great question. And interstellar travel is a topic I really am fascinated about. And I would hope that one day we have the ability to go to like through a wormhole or something, which basically that means that if you have it's like space folded together. So you have a little shortcut, just like Jodie Foster did in Contact, kind of travel really fast.
So we've got a young user, Lily,
All right.
wants to know how long does it take to get out of the solar system?
Oh, it depends how fast you're going. So Voyager, it's a great question. Voyager, those little probes that I was talking about that are going 1 million miles a day, 1 million miles per day. Think about that. That is really fast. That is they left Earth in about 1977 or 78. They're going to take they will not leave the solar system. The actual end of the solar system, where this cloud of comets is, in maybe another 50,000 years. So that is a very
Wow.
long time. Here's another example. To go that fast to get to our nearest neighbor, think about your neighbor just right next door. Our nearest neighbor, Proxima Centauri Alpha, this little star system, only 4.5 light years away. It would take us 70,000 years to get there riding on Voyager. So that just gives you an idea, hopefully, of how long it takes, how far everything is. Space is mostly space. That's the challenge is we go to the places that are beautiful and interesting and galaxies, and we can wish one way and the other with open space, but most of space is empty. And so we have to cross space to get from one end to get to different places. So that's the challenge. I think that's one of the biggest challenges we have is trying to harness the ability to do this if we really want to explore.
Since you mentioned open space again, Isaac has a question about open space.
Okay.
Why are the stars different colors
Yeah,
in
it's a
the
great
galaxy?
question. The stars are different colors. They're magnified a little bit in the program. You can always turn that down, but you can see them a little better. They have to do with the temperature of the star. So you have red giants, you have white dwarfs, you have yellow stars. It all relates to temperature of the star. So that's where the colors come from. And when you magnify it a little bit, you can see those colors. It's actually pretty nice. It's one of these things you can do in open space. You can tweak the setting a little bit. But yeah, good question.
We'll keep them going.
Yeah,
These
sure.
questions are great,
Yeah,
everybody.
they're great. I'm really enjoying this. This is a lot more fun than what I'm usually doing at this time.
So let's see. Matt is asking, what's your opinion on the origin of the repeating fast radio bursts heard
Oh,
recently?
the pulsars? I think they're pulsars, if that's what you're asking.
Okay.
I think that's what I'm not sure exactly which detection he's talking about, but these repeating fast. So I think what he's referring to is with SETI, with these telescopes, these radio telescopes. They've detected one. These telescopes are looking for alien signals. So how do you know you have a signal from an alien? One idea, and this was in the movie Contact and the book Contact, which was first a book, was looking for some translation of prime numbers, which would be a signal that this is a thoughtful signal sent back from an alien civilization. The other are these repeating signals. That maybe a repeating signal seems like more random than random electromagnetic radiation. So pulsars are stars in sort of their death throes that are orbiting. They're neutron stars, and they have a magnetic. It's like a magnetic field, and they orbit, and they have this repeating, like a lighthouse, repeating signal, and so it can resemble what we might think an alien civilization could be sending. However, when they've been detected, it's then uh, analyzed further to be probably a pulsar. So you have to rule out all of the other possibilities to then land on the possibility that it's aliens, unfortunately. So that is what I think it is without any other information to the contrary, I would say it's a pulsar, some pulsar out there.
Let's see. I've got Arvin,
Okay.
Arvin, Arvin. Hi, Arvin.
Hi,
Wants
Arvin.
to know why are people thinking about making Mars livable like Earth? I don't
So,
guess we're not trying yet to make
no,
Mars
no.
livable, but people are certainly thinking about it.
We're thinking about it because if you think about it's a really good question. So this would be terraforming. If we ever want to live, if you ever want to set up, so the idea is where are we going to go as a species? We can explore and come back. That's possible. We've done that with the moon. The first step for Mars will be orbiting it and maybe landing there. But in order to live there, to set up a colony beyond this planet, if that's what humans want to do, if they want to ever leave this planet, and eventually the sun's going to die or swell up to be a red giant, and eventually Earth won't be habitable for a number of reasons, we need to decide where to go. And Mars is the only planet fairly close to us, where it's possible maybe that we could set up a colony. The issue is that we can't. There's no oxygen. It's too cold, and there's no liquid water on the surface because there's no atmosphere because the solar wind has kicked off the atmosphere. So that's called. So then we think about how to transform the surface. So if we want to transform the surface so we can walk outside of our Martian house and go walk our Martian dog or whatever you have there, you want to breathe, and you want to, your dog wants to breathe, and you want to have grass maybe, and plants, because at least how we are designed, or how we exist now on Earth, if we want to have some kind of environment where we can go outside and not just be in some kind of space colony, where you're enclosed completely, like in Antarctica, for instance, where they have to be in a building the entire time. You need to figure out a way to get liquid water on the surface and have a breathable atmosphere. And it's easier said than done. I mean, there have been estimates I've read from 1,000 years, even fewer years than that, which I think is impossible, to millions of years to never. And that, think about what it takes. That we have to be able to control Mars to start building up greenhouse gases, but not too many, and then keep them there. How are you going to keep the atmosphere from leaving? Well, can we create a magnetic field, or do you just keep churning out the molecules with like little greenhouse factories? There are possibilities. There's even one idea of crashing an asteroid into Mars that has ammonia in it, so it blows out ammonia, which that sounds like an insane idea to me. But I mean, when you crash blowing things up and crashing body cosmic bodies together doesn't sound like the best option, but I mean,
Yeah.
there are many ideas. So this terraforming, this idea of, can you create another planet? There isn't any other planet. We should cherish this Earth where we have it. Is that there is no other place to go. It's not easily done or imagined that we will ever be able to, it's not going to be an easy move. We're going to have to think about who goes and all these other questions. But yeah, it's a great question about terraforming. Another really awesome topic to think about for the future work of our species.
All right. I think I've got two more questions to
As
pose
many
to
as you
you.
like. This is fun. I'm happy to
And
stay as long.
we're having a great time. I want to be respectful of everybody's time. It's getting on to 8 o'clock now, but Kim wants to know, do you think that there's life out there in some form that we've not yet considered or that would recognize?
Yeah, it's a great question. This is a great question. This is a question of, well, we say life is carbon-based and we say life needs water. What if it's not? And what if it doesn't? So what about that? And that's a great question. The problem with that is, how do you search for what you don't know? And that's one issue. It's hard to create an experiment to search for the unknown. I won't say it's impossible, but it's very difficult to design that, if you don't know what you're searching for. The second thing is that there are many reasons why we think water's best as a liquid. It has a wide range of temperature that it's liquid. Why carbon is a great element. And one idea out there, we've seen it in Star Trek, is silicon-based life. But there's more silicon than carbon on Earth, but yet life is carbon-based. And so there's plenty of opportunity for life to be silicon-based. There's a lot more silicon, but carbon is a better element. It creates stronger bonds, and there are lots of other reasons. And water, the other thing is, why do we follow the water? Well, water floats when it freezes. That's a really unusual quality for a liquid. Usually things, when they become solid, sink. If they float when they freeze, it means that anything alive under the water can survive. And there's evidence that, in fact, the Earth was covered in ice for a couple of times throughout its period where life is evolving billions of years ago, and several stages like massive ice ages, but they call it a snowball Earth, where Earth was frozen and the life underneath could survive. So maybe there's another molecule out there that's better, but we don't know about it yet. But it's true. What you're saying isn't wrong. It's that we can't prove that that's incorrect, that there's no other life that we don't know about. And certainly it's amazing to think about, for intelligent life, maybe there is a dimension that we don't even conceive of yet. I've thought, we can't even perceive life. And gets back to that Fermi Paradox, that maybe we're not ready. I mean, if you watch the movie 2001: A Space Odyssey, one of the best science fiction films, I think, the idea is that when humans have evolved to a certain point, they then are pushed forward to another part of their evolutionary path. And that was set up for them by extraterrestrials. And it's this, of course, it's science fiction, but it gets to this Fermi Paradox of maybe some kind of alien species knows about us but isn't interested in us. And there's no, I don't really think that makes a lot of sense from how we understand life, but who knows? And maybe there is something out there that's in another dimension. But what we do know is that life isn't plentiful. The galaxy is not teeming with life. And so that much we know, and we know that certainly the solar system isn't either. And so life seems it seems rare, at least for as far as we can see. And so it makes me think that life would be interested in knowing more about us. So I don't know. It's a great question, and there isn't really an answer, but who knows? I mean, yeah. I mean, I'd love to. It would be great if we found another kind of life, for sure. Sorry for that long answer, but
that was great. That was great. So
Thank
I'm
you.
curious, and I think we'll probably have to make this one the last question too.
Okay.
But right now, lots of folks are working at home or stuck at home. How does an astrophysicist continue to work?
Yeah, it's a great question. So as astronomers and astrophysicists, we're pretty lucky in that way. We're most of what I do is not at this wonderful telescope. When we're not under quarantine, I still only observe 2 or 3 times a year because these are big telescopes. We get a lot of data. And then the rest of the time, we're working on our computers and we have portable computers. And so, as it turns out, I do my day as far as work goes hasn't really changed all that much. Certain things have shifted online that weren't before, but we have a lot of digital capability now. But as far as the actual science and getting the work done, I still have a backlog of data that I can work on from anywhere. And that is one of the things I actually really like about being an astronomer too. I love being in the field, going to Mauna Kea, using these amazing instruments, and sharing the results with other scientists at conferences and colleagues and my students and everything. But I actually also really like having it all be portable and taking the data on my computer, my laptop, being able to use it, do it anywhere. So as an astronomer, it turns out that we can not our work isn't really in a lab that you think about with like microscopes and specimens and things like that, but really is data based. And so I'm looking at code. The spectra are all data based. The little image of the star I showed you, that's all data. So these are all files that I analyze right here where I'm sitting right now. In fact, when this virtual telescope isn't here, which I'm not showing you what's behind that picture, by the way, on purpose. But it's not as nice as what you see there, I think. But anyway, but yeah, it's good. So I hope everybody is able to, have a day where they feel like they're being productive. It's very challenging. I can't say it's not challenging, but and certainly the way we communicate has been certainly curtailed. And even as we all feel this as astronomers too, because we actually do have great sets of colleagues and everything. So everything is very different. But I do hope that everybody listening at least, has the ability to at least have a day that they feel is productive and is good for them. It's a hard time.
I see one more question. We'll
Sure.
do this one really quick
Yeah.
because I think this would be a fun one to end on, and it's sky watching.
Ah.
Uh, will you be watching Venus cross through the Pleiades star cluster this weekend?
Yeah. So disappointingly, I'm not a great sky watcher. Mostly, I get cold at night outside. Even I'm pretty wimpy there, but all my time in California. But I wasn't going to do that, but it is a great thing to do. And Venus is beautiful and bright. And yeah, I should have mentioned that you have the ability to be astronomers right outside when it's not cloudy, right outside your homes. And Venus is a perfect planet to look at. And you can think about the runaway greenhouse while you look at it, crossing through the Pleiades. And I will say with OpenSpace, you can then, the Pleiades, of course, is a constellation. So a constellation is our perception of where all these stars are. And with OpenSpace, you can turn on the constellations and see how they change as you leave the solar system. So that's fun to do. You could actually find the Pleiades and then move around it yourself. And even you could watch Venus and then you could do it too. So that's kind of a nice way to see the constellations in a different perspective. But that is really great. Pleiades is a nice little constellation to observe. And you might even see a meteor shower, or not a shower, a couple meteors, who knows? So those happen every night.
Rachel, this has been great.
Thank you, Chris. I hope everyone enjoyed it. This was really fun.
Based on the comments that I'm seeing, it looks like people had a great time.
All I hear
Learned
is
a lot.
applause, so we're good. No, I'm kidding.
Yay!
So, no, this is great. I hope it was fun.
And yeah, I would encourage everybody, if you're able, download OpenSpace, get a new perspective on the universe. And Rachel, thanks for bringing your
Absolutely.
insight, knowledge, and experience to us here at our virtual science cafe.
No, it was a lot of fun. It was a lot of fun. I hope to see everyone at the museum sometime in person pretty soon. I hope. Fingers crossed.
Yes, absolutely.
So, all right.
And hey, if not, everybody follow the museum on social media, Facebook, Twitter, and Instagram. Visit naturalsciences.org. There's a great new page that's set up that you can get from our homepage called Science at Home. There's do-it-yourself science activities, more videos. That's where we'll post when we have new live shows like this one coming up. We're going to keep trying to upload as much cool stuff to that Science at Home page at naturalsciences.org as we can to keep your science needs well met as we move through this. So naturalsciences.org, Facebook, Twitter, Instagram is where you can find all of us.
Thanks, Chris.
Rachel, we'll sign
Great.
off.
All
Bye,
right.
everybody. Thank you,
Bye,
Rachel.
everyone. Have a great night. Bye.
Take care and stay safe.
You too. Thank you.